Welcome to the second lecture on graph theory. In the first lecture, we have learned several definitions like graphs, subgraphs, connected graphs and components of a graph, and also we have learned what is a walk, what is a trail, path and all these things. So, please recall that a walk is a sequence of vertices and edges starting with a vertex and ending with a vertex, and a walk is said to be a trail if all the edges are distinct, not necessarily the vertices are distinct, and a path is a walk in which all the vertices are distinct, and hence automatically the edges are also distinct. So, we will start with trail, and in this today's class we will be talking about Eulerian trail and Hamiltonian cycle. So, we will learn what is a Eulerian graph and what is Hamiltonian graph today. Please recall that a trail is a walk in which all edges are distinct, but not necessarily the vertices are distinct, and a path is a walk in which all the vertices and all the edges are distinct. Okay, so let me give an example of a graph again. So, this is a graph with 5 vertices, and they are u, v, w, x, y, z. U and v are adjacent, v and w are adjacent, w and x are adjacent, y x are adjacent, z y are adjacent. There is a edge or loop z to z, and w z, v z, w y are adjacent, and v to y there is an edge. Now, here you can see that x y, z z, v, w, that means x y y to z and then z to z, z to v and v to w. This is a trail, because you can see that all the edges are distinct. So, this is the first edge, second edge, third edge, fourth edge and the fifth edge. So, this is a trail of length 5, but this is not a path. So, whereas x, y, z, v, w is a path of length 4. So, this is a path because you can see that all the vertices are distinct here and hence all the edges are also distinct, but this is not a path. This is not a path because here all the vertices are not distinct, only the edges are distinct. That is why this is a trail and this is a path. And next we move to the definition of Eulerian trail. Eulerian trail is a closed trail which includes all the edges of G. Okay, so, this is what the Eulerian trail is. And next we talk about more about this Eulerian trail. Let me talk about this famous problem which dated 1736. This is called Königsberg 7 bridge problem. So, I will draw a river. This is the Priegel river, and there are two islands. One is here, this is the second island here, and there are two bridges which connects this island with this side of the river, and similarly there are two bridges here also in this side. There is a bridge which connects these two islands, and there is one bridge here connecting this small island with this side of the river, and there is another bridge here which connects a small island with this side of the river. And so, what people attempt to find a route that would take them over each bridge exactly once and return to the starting point. Okay, so what they tried is to you start at some point and then you find a route which will take you over each bridge exactly once. You can't visit a bridge twice and you have to return to the starting point. But they could not find any route which can take them over every bridge exactly once and returning to the starting point. And finally, Euler in 1736 he proved that there is no such route, and the graph theory started with this problem in 1736. Okay, so let me just give try out one route maybe. If I start from here, then what I can do is that I can travel this way, and then come to this bridge, go this way, but I have to return to the starting point. So, I can go this way and return here, but this route does not visit all the bridges. So, these two bridges are left. So, this is what people tried to find a route that would take them over each bridge exactly once. This is important. You can't visit a bridge twice and return to the starting point. And finally, Euler showed that no such route exists. Okay. So, now if I can redraw this figure in terms of graph, let me label this, I will represent this as a graph problem. So, this is say 1, this is 2, this side of the river I label it 2, and this is 3, this island 3, this island 4, and I will represent this side of the river by a node label 1, this side of the river by the node 2, and 3 represent one island and 4 represent the other island. Now, I will represent these two bridges by 2 edges here. These 2 edges are corresponds to these 2 bridges, and 3 and 4 there will be an edge because there is a bridge between 3 and 4. Similarly, there will be an edge between 1 and 3, an edge between 3 and 2, and 2 edges between 2 and 4. So, this is a multi-graph basically because there are parallel edges here, multi-graph. Okay. So, now this problem is represented by a graph, by a multi-graph. Now, finding a route that would take them over each bridge exactly once and return to the starting point is equivalent to finding an Eulerian trail in the graph G. So, you look at the definition of Eulerian trail. Eulerian trail is a closed trail which includes all the edges in the graph G, graph or multigraph G. Now, the question is how do we characterize the graphs for which there is an Eulerian trail, or a graph which is having an Eulerian trail is called Eulerian. So, the problem is to characterize the graphs, the Eulerian graphs. Okay. Well, so this theorem will characterize Eulerian graph. A connected graph or multigraph. Multigraph means parallel edges and loop they are allowed. Multigraph G is Eulerian, if and only if every vertex has even degree. Okay. So, this is an if and only if condition. So, let me prove this theorem. So, I will be proving first this part, that means the graph G is Eulerian. So, let T be an Eulerian trail of G. So, we are proving this part, that we are assuming. So, the first part is that the if part, that means the graph is given to be Eulerian, and then we have to prove that the every vertex has even degree. Okay. So, the graph is Eulerian, that means the graph has a Eulerian trail. Let T be the Eulerian trail of the graph, the Eulerian graph given G. Okay. Then just I will illustrate this part by an example. Let me just take an example of an Eulerian trail. So, I will consider this graph. It has 6 vertices, and I label them as A, B, C, D, E and F. AB adjacent, BC adjacent, DC adjacent, DA adjacent, ED, EA, FA and FD, they are adjacent. Now, this is a graph, simple graph, it is not a multi-graph, and it is given that G is Eulerian. So, that means that this graph has a Eulerian trail. Let me consider this Eulerian trail. So, T is a Eulerian trail. So, I have to start at some vertex. Let me start at vertex A. So, A and then F, D, E, A, B, C, D, A. So, it is like A, F, D, E, then A, B, C, D, A. So, this is, you can check that this is a Eulerian trail, because it is a closed trail. It starts from A and ends at A, and all the edges are distinct, in between edges are distinct. Okay. Now, what I want to point out here is that now the claim here, that let me write down the claim first, that each occurrence of a vertex in T in the Eulerian trail contributes to the degree of the vertex. So, it says that each occurrence of a vertex, let me consider the vertex say D. So, each occurrence of a vertex in the Eulerian trail T contributes to the degree of the vertex. So, here D occurred, and this corresponds to 2 degree of D, because so while you are in the Eulerian trail, so you visit D, the vertex D, using the path, using the edge F D. This is, you enter to the vertex D and you leave the vertex D using the edge E. So, that corresponds to 2 degree of the vertex D, and again D occurs here, and here you enter to the vertex D using the edge C D, using the edge C D, and you leave D using the edge D A. So, that corresponds to again 2 degree contribution to the total degree counting of the vertex D. So, that is why each occurrence of a vertex in T contributes 2 to the degree of the vertex. Thus, degree of a vertex is sum of 2's only. So, it is even. Okay. So, this is the first part. We have proved that if the graph is Eulerian, then every vertex in the graph has even degree. Now, we will prove the other part, that we will assume that you are given a graph G where every vertex has even degree, and you have to prove that the graph is Eulerian. That means, you have to find an Eulerian trail in the graph. So, let me do prove that part now. So, this is the only if part we say. So, this part we will do in a way that you are given a graph where every vertex has even degree, and then we will talk about an algorithm to find an Eulerian trail in the given graph where each vertex has even degree. So, that is a construction proof, constructive proof. You just give an algorithm to find Eulerian trail in the given graph. So, here is the technique to find Eulerian trail. So, you select a vertex, and form an Eulerian trail starting at that vertex. Okay. So, this is the algorithm is called Flewer algorithm. So, this is how we find an Eulerian trail in the given graph. What we do is that at each step we move across an edge whose deletion does not result in more than one component. Unless we have no choice. And at the end of the algorithm, there are no edges left, and the sequence of edges we moved across form a Eulerian trail. I will explain this technique using an example. So, it says that at each step we move across an edge whose deletion does not result in more than one component unless we have no choices. At the end of the algorithm, there are no edges left, and the sequence of edges we moved across form a Eulerian trail. Let me illustrate this algorithm using an example. I will take a slightly bigger example now. There are 8 vertices in the graph. This is again A, B, C, D. This is E, this is F, G, H. A, B, BC, DC, AD, they are adjacent. Similarly, here FA, ED, EA, FD, they are adjacent. BG, CH, CG and BH, they are adjacent. So, you are given this graph with 8 vertices, and you can see that every vertex has even degree. So, A, B, C, D, they are having degree 4, E, F, G, H, they are having degree 2. So, it says that you select a vertex. So, let me select vertex A, for example. I select vertex A, then we move across an edge whose deletion does not result in more than one component. So, I can move across F, I can use this edge to move, and I delete this edge from the graph. So, this is my first visit. If I delete this edge, the number of components does not increase, the graph remains still connected. From there, from F, I can go to D only. So, I move across this. So, this is my second move, and I delete this edge. Then of course, the number of components increases, because now F is an isolated vertex, but I do not have any other choice. So, unless we have no choices, we can do that. So, the second move is to D, and from D we can go to E, and I remove this edge. This is the third visit. This is the third edge that the Eulerian trail visits, and then E to A, and I remove this edge also. This is the fourth. I am just writing the sequence in which we are visiting different edges of the graph, and at this moment we are at A, and then I move across this edge, and then I move across this edge, then I move across this edge, and when I reach to B, so this is where you need to be little more careful. Like now from B you have many choices, you can go to A, you can go to G, you can go to H, but the algorithm says that you do not go to A, because if you go to A, you increase the number of components. So, this will be removed, and but you have other choices. You have the option of going to B to G, B to H. So, you go there. If you go to G, that does not increase the number of components. So, here instead of going from B to A, you go to B to G. So, this is the 8th move, and from here you can next go to C. This is the 9th move, and you are here now in C, and then you go to this edge, and then you go to this edge, 11th, and now you go to A back, because finally you have to go to A again, because you are creating a Eulerian trail. So, this is how you can, and the sequence, and finally you see that at the end of the algorithm there are no edges left, and the sequence at the sequence of the edges we moved across form a Eulerian trail. So, this is you just write down this sequence like A, then F, D, E, A, D, C, B, G, C, H B A. So, this is the Eulerian trail that is given by the Flewer algorithm. So, we have learned how to characterize Eulerian trail or Eulerian graph. A graph is Eulerian if and only if all the vertices are of even degree, and we have proved that theorem. Thank you very much for your attention.